Welcome into the 10th week of the open course on diffusion in multi-component solids. This is the 42nd lecture in this series, and in this lecture I will talk about how self and impurity diffusion coefficients are experimentally measured. Since at times there is much confusion about various diffusivity terms in the literature, I will first summarize all kinds of diffusion coefficients which we have already studied at different points in this lecture. This will help in clearing the confusion that usually happens in using various diffusivity terms. We have gone through the theory of diffusion. First we looked into the phenomenological aspect of diffusion, then we went into details of the atomistics of diffusion, we looked at the atomic mechanisms of diffusion, and also we analyzed the diffusion process in terms of the atomic jump frequencies, which helped us to establish a correlation between the phenomenological coefficients and the fundamental atomic jump frequencies. Next few classes I would like to take you over various experimental techniques that are used for determination of different types of diffusion coefficients. Now when you look into the literature on diffusion, you will come across various kinds of diffusivity terms, and at times it is confusing. Most of these diffusivity terms we have already covered at different points in this class, but to summarize I will briefly explain these different types of diffusivities which are used. The most fundamental is the self diffusivity or the self diffusion coefficient. It essentially refers to the diffusion of an atom in its own pure lattice. So it refers to the diffusion of A in pure A. Second diffusivity is called the impurity diffusion coefficient. This is also referred to as solute diffusion coefficient. And as the name suggests, impurity diffusion coefficient is the diffusion coefficient that characterizes the diffusion of an impurity atom in a homogeneous host lattice. So we can define this as diffusion of A impurity in host lattice of B. Now the self diffusion and impurity diffusion are essentially the diffusion phenomena that occur when there is negligible concentration gradient. That is, these terms characterize the diffusion in a homogeneous alloy. Now when there is concentration gradient present, then we also need to take into account the cross effects of different concentration gradients which we have gone over, and then we have to define different diffusivity terms. So when the concentration gradients are present, we would like to define interdiffusion coefficients. Now whenever there are concentration gradients present, in presence or absence of external driving forces, there will also be some drift associated with it. For example, we have seen even in the absence of any external driving force, if the molar volume varies with composition, more precisely if partial molar volume of components vary with composition, then there will be a drift because of the net volume flow, and hence in such cases we need to first fix the frame of reference. I have explained various frames of reference at the beginning of this class. So, when we talk about lap fixed frame of reference, the flux is measured with respect to a frame which is stationary. So, different frames of reference we have talked about. The most widely used of it is the lap fixed frame. Now, if we fix the frame of reference at the local center of volume, so that the net volume flow is 0 at any plane, it is referred to as volume fixed frame of reference. So, we can also measure the flux with respect to volume fixed frame, and the diffusivity is measured with respect to that would be the diffusivities with respect to volume fixed frame of reference. This is also referred to as RV, and typically for the assumption of constant partial molar volume, the volume fixed frame coincides with the lap fixed frame. We can also define with respect to local center of mass or with respect to local center of number of moles of the components, and those are called mass fixed frame or number fixed frame, and so on. So, those are denoted as Rm and Rn. We can also determine the flux with respect to a frame of reference which is fixed to a particular lattice plane, and it is referred to as intrinsic diffusion, and the diffusion coefficients evaluated with respect to lattice fixed frame are called intrinsic diffusion coefficients. And this is with respect to lattice fixed frame. This is also known as Kirkendall frame of reference. Okay. So, these are various types of diffusion coefficients that we typically encounter. So, again the self and impurity coefficients basically characterize the diffusion in a pure substance or in a homogeneous alloy. So, in pure substance or homogeneous alloy, and the interdiffusion and intrinsic diffusion coefficients, they characterize the diffusion behavior of different components when there are concentration gradients present. So, note here, although the interdiffusion coefficients and intrinsic diffusion coefficients characterize the diffusion behavior in presence of concentration gradients, these coefficients are not functions of concentration gradients, but they are functions of composition only. In order for them to be material properties, they have to be functions of composition. If they depend upon concentration gradients, then they will not be a material properties, and as we have seen through the theoretical relations as well as experimentally, it has been shown over several systems, these are the functions of composition. So, whenever there is a concentration gradient present at each x coordinate, since the composition is different, the set of diffusion coefficients that we need is different, but still this set of diffusion coefficient depends upon composition and not the concentration gradient. That means, if we are dealing with the same composition, no matter what is the concentration gradient at that composition plane, the set of diffusion coefficient should be same. Look into some of the experimental techniques that are used for characterizing these various diffusion coefficients. Let us start with the self and impurity diffusion coefficient in today's class. So, for determination of self or impurity diffusion coefficient, we can make use of solution to the diffusion equation that we derived in lecture 20 of this class. If you remember, we dealt with the boundary conditions of instantaneous planar source, which is presented here in this diagram. So, we have in this case a thin layer of A deposited onto a surface of pure B. Now, this thin layer is really thin, so that its thickness can be assumed to be 0. If this assembly is annealed at a fixed temperature for certain time, A will diffuse into B and then it will develop some kind of profile like this, and we have derived the solution for this. So, if we want to find the concentration of A at any position x at any time t, we can use the solution delta over root by dt exponential minus x square over 4 dt, where x represents the distance coordinate, that is the distance from the surface on which A was initially deposited. So, x equal to 0 is taken on the surface where A was initially deposited. Now, this solution was valid for infinite boundary condition, which means it is assumed that the diffusivity and the diffusion time are such that this diffusant A does not penetrate all the way to the other end of B, and so for all the practical purposes the other end can be assumed as x equal to infinity. Then this parameter delta is nothing but the amount of A deposited per unit area initially, and if we consider unit cross section, it is assumed that throughout the thickness of B, that amount delta remains the same. So, this solution can be used for getting the value of D for A in B. To simplify this, if we take the logarithm on both sides, we get ln C is equal to, now this delta is constant, we assume D is constant, only for that assumption we can derive this solution. So, this is constant, so we can assume ln C is equal to k minus x square over 4 dt. So, this is an equation of a line. If we plot ln C versus x square, we will get a straight line with the slope of minus 1 over 4 dt. T is the diffusion time here. So, if we plot ln C versus x square, we will get the plot to be a straight line whose slope is minus 1 over 4 dt. We know the diffusion time t, and by determining slope we can get the value of d, and this refers to the value of diffusivity of A in B. First, we assumed for this solution that D is constant. We know D is a function of composition. So, for this assumption to be true, one condition may be that the concentration of A throughout this diffusion profile has to be very small, and since the concentration throughout is very small, the variation in D with x is not significant, and then we can apply this solution. This is true if the initial thickness deposited of A is very small, close to 0. Now, when this is true, we are dealing with diffusion of A in a very dilute solution of A in B. That means we are dealing with impurity diffusion of A in B. So, with this geometry, what we are going to get is the impurity diffusion coefficient of A in B. Now, second practical aspect, since the concentration at every plane is very small, how do we determine these concentrations? Because we need to determine concentrations at many sections, at many values of x. Typically, the tools that we use for measurement of concentrations like EPMA, they do not have resolution required for determining these concentrations. So, at each plane the concentration is going to be less than ppm. So, how do we accurately measure these concentrations? Normal tools will not be able to do that, and hence for these experiments radio tracers of A are used. Why radio tracers are used? Because they emit gamma or beta rays, and the count rate of the emission can be very accurately and precisely be measured. And since we use the radio tracers, the diffusion coefficient so determined is commonly referred to as tracer diffusion coefficient. So, if we want to describe a typical experiment, so if we want to determine the impurity diffusion of A in B, this may be pure B or it can be a homogeneous alloy in which A is an impurity, right. So, it can be, for example, diffusion of copper in pure nickel, or it can be diffusion of copper in a nickel zinc alloy. Now, of course, the impurity diffusivity will be different in both the cases, but both are characterized as impurity diffusion coefficient of copper in that particular lattice or in that particular alloy. So, we take the substrate of B, its surface is metallographically polished very well, and then a thin layer of radio tracer A is deposited onto the polished surface. The radio tracer is usually denoted by the symbol star, and then the diffusion is allowed to progress by heating the assembly at the desired temperature for desired time. So, A diffuses inside. After the desired annealing time, the sections are cut perpendicular to the diffusion direction, thin slices are removed, and specific activity of A star, is measured in each slice, and the specific activity, which is written as A, is plotted as a function of x square, that is the square of the distance from the surface. The specific activity is directly proportional to the concentration of A star, and so we can write A is equal to K times C, and since there is a direct proportion, we can very well plot ln of A versus x square instead of ln of C versus x square, because in both cases the slope should be same. So, by plotting ln of A versus x square and by determining the slope of the plot, we can get to the tracer diffusivity of A in B. It is usually denoted as dA star in B, is the impurity diffusion coefficient of A in B. So, this tracer diffusivity refers to the impurity diffusion of A in B. Now, there are various ways in which the deposition can be done. The deposition of radio tracer can be done by either physical vapor deposition, that is by evaporation, or It can be done by electrodeposition, or it can be done by applying a solution of A star onto the surface and drying. Similarly, there are various ways in which the sectioning can be done after the diffusion experiment. If the diffusivity is larger, a large enough diffusion zone is created, and so we can go for mechanical sectioning. If the diffusivity is very small, so that a very small diffusion zone is created, then one has to take the help of ion beam sputtering. Now, coming back to this geometry, here we talked about determination of diffusivity of A star in B. What about self diffusion? Self diffusion is basically the diffusion of A in pure A. Now, how do we identify or how do we trace particular atoms of A in pure A, because all the atoms of A are indistinguishable. Here again the radio tracers or radioisotopes come to our help. So, for determining self diffusivity, we start with the substrate of pure A and deposit a radioisotope of A on top. Now, the radioisotope is almost similar to the normal isotope of A, except that it has a different mass. So, it is going to exhibit almost the same diffusion behavior as that of the regular isotope of A, and hence A star in A will characterize the tracer diffusion, which can be taken as self diffusion coefficient of A. So, for self diffusion measurement, we have this type of geometry. Deposit a thin layer of A star on A, rest everything is same. We determine the specific activity of A by sectioning and plot ln of A versus x square to give the self diffusivity of A, that is dA star in A, and this is the self diffusion. Now, this dA star is not exactly the diffusivity determined by Einstein's equation, which is given as 1/6 gamma lambda square in any cubic lattice, but we can relate it to the experimentally determined dA star by applying the correlation factor f. We have talked about this correlation factor f, and we have even derived correlation factor in some of the cubic lattices, and this is a geometric factor. Now, I would like to show some examples from the literature on experimental determination of tracer diffusivities. The first example is from the work reported by Peterson and Rotman back in 1970 on impurity diffusion in aluminum. They have reported various tracer diffusivities in aluminum. I would like to take the example of impurity diffusion of cobalt that they have reported. They used cobalt 60 isotope for this. They deposited this cobalt isotope by evaporation on the single crystal aluminum substrate. Using single crystal aluminum gives precisely the bulk impurity diffusion coefficient, because there is no interference from grain boundary diffusion. These are the profiles of specific activity versus distance square as they have reported. Now, these data points may be a little bit inaccurate because I have extracted the data from this paper and replotted here. Also note that the straight lines that I have shown are only indicative, they are not the actual fittings. So, you can see they have done the experiments at various temperatures, including 654 degree centigrade, 614.9 degree centigrade, 573 degree centigrade, down to 421.8 degree centigrade. most part of each data set can be fitted by a straight line as expected. However, near to the surface, that is close to x equal to 0, we can see each of the plot deviates from the straight line and it shows some upward curvature. And the reason for this, as they have mentioned, is because of the oxide layer that quickly tends to form on aluminum surface. So the tracer which is deposited on this oxide layer has to first diffuse through this oxide layer, and the diffusion through this oxide layer is very slow, and hence the initial part of each of the curve shows an upward curvature here. However, they fitted the later part with a straight line, which essentially gives the impurity diffusion of cobalt in aluminum. By determining the slope, we can get to this d star of cobalt in aluminum. With this, the diffusivities determined at various temperatures as reported by them are presented here in this table. We can see over the temperature range of about 421 degree centigrade to about 654 degree centigrade, the impurity diffusion of cobalt is varying over 3 orders of magnitude. With this, they also evaluated the activation energy for impurity diffusion of cobalt in aluminum, which comes out to be about 174.5 kilojoule per mole. Now, I would also like to present a very recent report on tracer diffusion experiments. This is from the work of Vaidya and group. They determine the tracer diffusion coefficients of all the constituent elements in the quaternary cobalt chrome iron nickel and quinary cobalt chrome iron manganese nickel alloys at the equimolar concentrations. These are very popular these days. They are referred to as high entropy alloys, and diffusion is one of the most debated topic in these high entropy alloys. So they determined the tracer diffusivities of each of the constituent elements in these two alloys. Here I am showing the plots of cobalt 57 isotope activity versus distance as presented by them. Again, the data points may be not very accurate because I have extracted the data from the paper and replotted here. We can see on this plot of specific activity versus distance, there are two distinct slopes on this plot. The first part refers to the bulk diffusion, which is characterized by a higher slope. Since the slope is minus 1 by 4 dt, higher slope refers to the lower diffusivity. The latter part corresponds to the grain boundary diffusion, because they conducted the experiment in polycrystalline materials. So it is also possible to determine the grain boundary diffusion. So they have done it. I will not discuss it here. I will just focus on the bulk diffusion. So they plotted the bulk diffusion portion. So specifically for cobalt, I have shown here at 3 different temperatures. Again, the data extracted and replotted here. Just like the last plot, the solid lines here again are not the actual fittings, but they are just indicative. We can see this data can be fitted with a straight line, and hence the tracer diffusion coefficient of cobalt can be determined in this alloy. This I have shown in the iron nickel cobalt chrome manganese alloy. Now, since cobalt is also a part of the host lattice, this will be referred to as self tracer diffusion coefficient of cobalt in this particular high entropy alloy. With this, they determine the activation energy of cobalt to be 270 kilojoule per mole. They have also done the experiments of tracer of each of the constituent element, and in this particular quinary system, the activation energies that have been reported by them are listed here. So they used cobalt 57, chromium 51, manganese 54, iron 59 and nickel 63 isotopes. You can see the activation energy of cobalt is the lowest, whereas activation energy for diffusion of chromium is seen to be the highest. So, these are some of the examples that I have shown from the literature, and this was about the determination of self or impurity diffusion coefficients by tracer technique. In the next class, we will talk about interdiffusion.